Welcome back to the Deep Dive. Today, we are putting on our metaphorical safety goggles and looking straight up. Our mission is pretty straightforward. We're diving into the hidden tech that keeps everything in the sky safe. We're talking massive commercial jetliners, moving millions of people, right up to sophisticated rockets heading for other planets. How do they handle extreme stress?
Well, it really is the ultimate high-stakes environment, isn't it? When you get into aerospace, the level of testing required. It demands perfection. The margin for error, it's basically zero, which means the data, the information they use to build these things, it just has to be perfect, unimpeachable.
Absolutely. Yeah, we've been looking at sources that detail the really fundamental role of precision load cells, sensor technology in this whole industry. We're focusing specifically on a partner whose legacy, believe it or not, goes all the way back to 1968. So our mission for you today is to unpack where these sensors are used, and some places might surprise you, and how they achieve that extreme, non-negotiable accuracy needed for flight, and also why the giants, NASA, Boeing, Airbus, why they rely on this specific proprietary technology.
And what's fascinating, I think, is getting the context for all this testing. Every single component, literally everything that goes into a flight vehicle. Think about a main wing assembly, or even just the hardware mounting an engine. It all has to be tested. For fatigue, for stress, for ultimate performance under intense forces, sometimes rapid changes in force, temperature too. These precision systems, they're the critical, often unseen infrastructure. They verify every single design calculation, every manufacturing tolerance.
Okay, right, let's unpack that. Because when you say testing, I think most people imagine maybe a final check, But the sources show the sheer variety of uses across the entire design life cycle. It's kind of stunning, actually. It's definitely not just about measuring the overall weight. So what exactly are engineers measuring with this level of precision, and why is it so complicated?
Well, we're really talking about the four core pillars for validating performance. You've got thrust, torque, static loads, and fatigue endurance. These measurements dictate basically everything, from how efficiently an engine creates power to calculating the exact number of flight cycles a wing can handle before metal fatigue becomes a real danger. And the difficulty, it lies in getting that highly precise, repeatable data while you're subjecting the thing you're testing to, simulated chaos.
That structural evaluation piece sounds critical. The source material details some really comprehensive ground-based testing. It sounds absolutely massive, Herculean even, like applying millions of pounds of force over and over to an aircraft wing just to simulate its entire lifespan. That's the famous wing fatigue testing, right? That's the one. Or subjecting a huge rocket structure to really complex compression and tension forces, mimicking launch.
Wow.
Yeah. And think about the implications for the biggest test articles. A structural rocket test, for example. It's not just one static load. You're applying forces that mimic the sheer violence of liftoff, maybe orbital maneuvering too. These sensors are absolutely critical there. But they're also essential for the, let's say, more granular scenarios. Still life or death stuff, mind you. Okay, give us an example. What's a granular but still totally essential test that needs this kind of extreme fidelity?
Landing gear evaluations. Think about it. That component is literally designed to absorb the kinetic energy of a massive vehicle hitting the ground. Fast. You need incredible accuracy when you measure the loads going through that gear during simulated impacts. And you absolutely have to ensure the gear itself doesn't go past its structural limits. It's the difference between a safe landing and, catastrophic failure on the runway.
Right. And beyond just the airframe, the sources also mention crucial engine hoist tests, wind tunnel experiments for aero efficiency, and evaluations for smaller vehicles too. Helicopters, even parachutes.
Exactly. It's about verifying every critical detail, the design, the materials, the assembly, all the way through.
So if we connect this to the bigger picture then?
It explains why this tech is so deeply embedded. It validates absolutely everything. But here's where the applications get maybe truly surprising. We're talking advanced stuff. Out-of-atmosphere applications that this proprietary tech supports.
That's the part that really caught my eye too. We're talking about prepping for space missions now, not just commercial flights.
Precisely. The sources specifically highlight using these load cells in things like reduced gravity simulations and spacewalk simulators. Just think about that challenge for a second. They're using these super precise sensors to measure the forces an astronaut exerts during a simulated spacewalk, often in a giant water tank,
So they're not just measuring a static object. They're measuring dynamic human movement in this engineered environment that's supposed to mimic near zero friction space. Is that right?
Exactly right. You need incredibly reliable measurement when you're trying to copy conditions that are just totally unnatural here on Earth. The data these sensors capture, it tells NASA how to design handholds, how much force an astronaut can use without floating away, the ergonomic limits of the suits themselves. And these sensors also play a part in in-flight data acquisition systems, getting real-time info back to engineers while the vehicle, maybe a prototype jet, maybe a rocket stage, is actually performing.
That brings us perfectly to the core question, doesn't it? How do they achieve this reliability? Especially when the test environment is so, well, volatile. You could be talking freezing high-altitude simulators or a pressurized clean room during manufacturing. What makes these specific load cells reliable enough for companies designing space travel?
Well, the core proprietary tech is really designed specifically to beat interference. When you're measuring forces on, say, a rocket structure, you're fighting all sorts of things. Noise, vibration, big temperature swings, standard sensors. They often just can't handle that environment reliably.
And the sources point specifically to two critical design features. They're moment-compensated and temperature-compensated load cells.
Okay, for someone listening who hasn't maybe worked with strain gauges before, what does that compensation actually solve for the engineer running the test? Good question. Let's start with moment compensation. Imagine a typical load cell is like a bathroom scale. If you stand right in the middle, you get an accurate weight. But if you stand way over on the edge, the reading might be off because the force isn't centered, it's eccentric. Moment compensation fixes that. It means the sensor measures the force accurately even if the load isn't perfectly centered on it. In huge structural tests where you've got these immense, sprawling wing assemblies, you just can't guarantee perfect load alignment all the time. Moment compensation makes sure the data stays true.
Okay, that sounds like a huge practical advantage in a real-world test setup. And temperature compensation, I'm guessing, deals with the extreme heat from an engine test or maybe the deep cold of a high-altitude simulation.
Exactly. Temperature naturally makes metals expand or contract, right? And that fundamentally changes the electrical resistance in the measuring element inside the sensor. That causes data drift. Temperature compensation corrects for that drift internally, automatically, so the measurement stays stable regardless of the thermal environment.
Okay, but here's the biggest technical nugget, maybe the real aha moment for me: the internal construction. These proprietary alloy strain gauges, they don't just use the standard setup of maybe 2 or 4 gauges. They use 8 per sensor. That sounds like overkill, maybe, until you think about the stakes involved.
It really is the definition of engineered redundancy and precision. Think of it like this. A standard sensor might have 1 or 2 witnesses reporting the load, this proprietary design. It has 8 highly specialized witnesses, all cross-checking the measurement at the same time. So if one gauge is momentarily affected by, say, a vibration spike or a sudden temperature change, the internal setup uses the other 7 to correct that data point instantly. That's how you guarantee reliability when the failure of just one component's measurement could potentially lead to a catastrophic design flaw down the line.
Right, that makes the proprietary alloy itself incredibly critical then, because if you're using 8 of them, they all have to perform identically, right, even under massive stress. So what's the technical payoff? Why pack so much proprietary measurement hardware into one single cell?
It comes down to the output signal. The source explicitly mentions this design provides a reliable 4 millivolts per volt output. And why should you, the listener, care about that? Well, you should care because that consistent, high-fidelity output signal is incredibly robust. It's very resistant to electrical noise.
So less static on the line, basically.
Precisely. In these huge test facilities, you might have cables running from the load cell, which could be buried deep inside a wing assembly, or sitting near a massive rocket engine all the way back to the data acquisition system. Hundreds of feet sometimes. A lower quality signal would degrade over that distance or pick up electrical interference from other equipment. That leads to noisy, unreliable data. This powerful 4 mV output ensures the signal stays clean, stays reliable, stays high resolution. It delivers the extreme accuracy needed in these mission-critical environments.
So the answer to why is this proprietary system non-negotiable for aerospace? It isn't just accuracy alone, it's accuracy plus reliability under really tough conditions.
Absolutely. You just cannot afford data drift. You can't. When a major defense contractor or NASA is relying on this data to sign off on a billion-dollar vehicle, the measurement has to be rock solid, period. The internal compensation plus the redundancy from those 8 proprietary gauges, it ensures the data accuracy stays true even under the maximum stress conditions that really define this industry.
Okay, That transition leads us perfectly into the full life cycle of a flight vehicle. Because it's clearly not just about final flight testing. This technology seems woven into the entire manufacturing process, right from initial R&D to the moment the vehicle rolled off the assembly line.
Yeah, it's fully integrated. These sensors guide engineers and manufacturers through literally every stage. They aren't just used to test the final product, they're used much earlier, to validate the tooling they use, to confirm the materials meet spec, to ensure individual components are right before they're even assembled. The data validates their process at every single step. It creates the sort of digital thread of quality assurance.
Right. To give you a concrete picture, we're talking about testing individual landing gear parts, massive carbon fiber wing sections, even complex engine mounts, using these sensors before the airplane even looks like an airplane.
Exactly. The sensors provide those non-negotiable insights that ensure every single component performs safely and efficiently.
And the proof of this necessity, I guess, is right there in the customer list mentioned in the sources. The sheer number and who they are. The companies relying on this proprietary tech really speaks volumes about its established quality and reliability. Global aviation.
Yeah, we're talking about basically every major player you can think of. Boeing, Airbus, Lockheed Martin, Northrop Grumman, Bombardier, Embraer, Gulfstream, and NASA, Cessna.
Wow. That roster basically represents the entire ecosystem of global flight technology and space exploration. That kind of reliance really underscores the non-negotiable quality and standardization that's required in this industry.
And this is exactly where quality assurance separates just an everyday vendor from an essential, trusted partner. This is why things like accreditations matter so much.
Okay, let's talk about those. The sources say they're accredited by A2LA to ISO IX 14051 1.2017 and ANSI CSL Z540R1 1994 standards, and all products are designed, tested, and calibrated at their facility in Arizona. So why should the average person care about a string of numbers like ISO IX 12021.2017?
You should care because it's basically the global gold standard for calibration labs. Achieving that ISO IX 17025 accreditation, it's incredibly difficult. It takes a lot of time and effort. It means that the facility itself, the people working there, the equipment they use, the processes they follow, has been audited by an independent third party and proven competent to generate accurate, traceable data. That traceability is key.
Okay, so it's not just that they claim their sensors are accurate, they have globally recognized proof that their method for determining accuracy is reliable and sound.
Precisely. So if Boeing builds a plane in Seattle using data calibrated in Arizona, and maybe Airbus relies on similar data over in Toulouse, that ISO accreditation acts as a kind of universal language of trust. Every single sensor goes through this rigorous, accredited calibration process to meet and often exceed aerospace industry requirements. It's the final guarantee that the resulting data is trustworthy, which, at the end of the day, is the ultimate prerequisite for keeping passengers and missions safe.
And finally, the sources mentioned they offer a complete measurement toolkit, covering pretty much every possible challenge, it seems, ranging across different product types, from tiny miniature sensors for delicate tests all the way up to jumbo low-profile models, multi-axis sensors for complex force mapping, torque transducers, even advanced wireless and digital instrumentation. They're providing the whole solution package.
Right, whether it's measuring a tiny component on a drone or mapping the massive thrust from a brand new space launch system, that underlying commitment to calibration and quality control ensures the data is always trustworthy.
Okay, so let's wrap up our deep dive for today. We've established the critical, really massive role these sensors play. Ground-based testing, space prep testing. We looked at the technical precision they achieve through that proprietary design, the moment and temperature compensations, and of course those 8 robust strain gauges per sensor. That's pretty impressive.
Yeah.
And the wide adoption by pretty much every major global aerospace company and space agency. It cements a legacy of reliability going back, over 50 years now?
So what does this all really mean for the advancement of flight? I think the sources clearly demonstrate that the silent, precise work of these load cells and sensors, it's the unsung prerequisite for every single step forward in flight technology. They manage the risk, they verify the complex calculations, they ensure the structural integrity of vehicles that operate under just unbelievable conditions. That legacy in aerospace, it's built on 5 decades of precision, performance, and partnership. It enables progress that, honestly, we often take entirely for granted every time we step on a plane or watch a rocket launch.
That's a perfect summary. And for you, our listener, here is a final provocative thought to mull over based on all this. Given that these systems are used not just for flight testing, but also in those reduced gravity and spacewalk simulators, things that directly impact astronaut safety and efficiency, How might the continuous evolution of these sensor technologies directly dictate the structural design limits for humanity's next giant leap into deep space exploration? Could the next generation of super reliable, temperature-compensated load cells be the key that unlocks our ability to safely design and build the first truly deep space exploration vessels? We'll leave that thought with you. Thanks for joining us on the Deep Dive.